Hello a croeso. Hello and welcome. My name's Rob Wilson, and I'll be introducing this short video on behalf of the School of Mathematics at Cardiff University to illustrate how some relatively straightforward ideas from pre-university mathematics can very quickly be developed and built upon to lead to a world of infinite possibilities. The problem we are going to consider is the Koch snowflake. Our starting point is an equilateral triangle of side length equal to 1, and then introduce a series of repeated iterations and investigate the patterns that emerge. So starting with our triangle, we can split up each of the sides into 3 equal parts. The middle segment of each of the sides can then be used to create a new, smaller equilateral triangle. Repeating this process again and again and again leads us to a sequence of fascinating shapes which we can now start to analyze. In particular, let's investigate what happens to the perimeter of these shapes. We're going to record the following pieces of information at each iteration, at each step. And in particular, we're interested in what happens to the perimeter as the number of iterations gets larger and larger. The first stage is relatively straightforward. Obviously, we have 3 sides in our triangle, and the length of each side, as we've already described, is equal to 1. So the perimeter is just 3. At the next stage, at our first iteration, remember we are splitting the sides of the original triangle into thirds, so that each side represented at this stage is of length a third. Putting this information into our table, remember the diagram here represents one side of our initial triangle. Therefore, the total number of sides is 3 times 4. The length of each side we know is a third, and so the perimeter is given by multiplying the previous 2 columns together. What happens at the next stage? Well, again, each of the sides of the previous iteration are split into 4 different sides. And having the previous case, where each side was equal to a third, because we've split each of those sides again by a third, each of these new sides is of length a third times a third, or 1 over 9. Now, as we repeat this information time and time again, we can start seeing the patterns that are developing. And in particular, we recognize that in general, after n of these iterations, this result will tell us the perimeter of our shape at that step. So if we took the 10th iteration, we'd be able to determine what the perimeter of that shape was at that point. But what happens as we keep repeating, as we keep adding to the number of iterations within this process? Well, let's look at the formula in a bit more detail. The term in the bracket, the 4 over 3 to the n, we can write out as a multiple of terms. And the key thing to notice is that every term in the bracket, 4 over 3, is bigger than 1. So at each stage, we are multiplying our perimeter by a number which is bigger than 1, which means as we increase the number of iterations, as it gets larger and larger and larger, the perimeter of our shape is going to tend to infinity. It's going to get infinitely big. So it's going to grow and grow and grow without bound. That in itself is a really interesting idea. This idea of infinity is certainly something that you'll be introduced to at university and explored in far more detail. So let's look at another aspect of this particular process. And let's calculate the area of the shapes at each step. So we're going to record the iteration, the number of new triangles that are produced, the area of each of these new triangles, and then the total area of the shape at each step or iteration. So our starting point again is our equilateral triangle. And in this particular case, we can work out the area. You can use any formula that you wish. And the area is 4.3 units squared. Now we're going to refer to this area as A. Hopefully this will help us when we come to analysing and investigating some of the patterns that might emerge. So for our first iteration, remember we're introducing new triangles on each of the sides of the original triangle, whose base length is 1/3 the length of the side of the original triangle. So we know that there are 3 triangles in this case. And the area of each of these triangles is going to be 1/9 the area of the original blue triangle. One way of illustrating this, or thinking of this, is to see how the red triangles will tessellate. Another interesting topic. But it'd be interesting to see how the red triangles tessellate on top of the blue triangle. And you'll see you can fit 9 red triangles into the blue triangle. So putting this information into our table, we can determine the total area as the area of the original blue triangle plus 3 times the area of one of the red triangles. The next iteration, we can see that there are a total of 12 new triangles. And similar to the previous case, the area of each of these green triangles is going to be 1/9 the area of the red triangles. And we know the area of the red triangles was 1/9 the area of the original blue triangle. So putting that together gives us the area of each of the green triangles as A divided by 9 squared. So putting this information into our table, we can start seeing potential patterns emerging. We may have to include an extra step, which you can do, and record the corresponding results. But once again, we're interested in analysing the patterns that emerge. And again, what happens as the number of iterations gets larger and larger and larger? So looking at this general expression for our area, hopefully you can recognise a particular pattern that's emerging from one term to the next. That is multiplication by 4/9. And that represents a geometric progression with common ratio of 4/9. So using that information, we can sum the first n terms using a well-known formula for a geometric progression. And after some relatively straightforward manipulation of that expression, we can see that again, we have a term involving n. Now in this case, the number in the bracket, 4/9, is less than 1. So as n goes off to infinity, as n increases, that number in the bracket is going to get smaller and smaller until it tends to 0. In other words, the area of our shape, as n gets infinitely large, as the number of iterations gets infinitely large, is finite. So let's just stop and think about what we've shown. We looked at sequences. We looked at patterns that were emerging from the sequence for our perimeter. And the perimeter of our shape, as we repeated the same process time and time again, went off to infinity. So the distance all the way around our shape, as we did infinitely many iterations, was infinite. However, repeating the same process leads to a shape with a finite area. So a shape with a finite area has an infinite perimeter. Now that may take a bit of getting used to, but these are just some of the key ideas that can be shown with some relatively straightforward mathematics. And all the mathematics we've used here are sequences and series. Now it turns out that that particular example falls under a far larger body of work known as fractal geometry. And fractals are the study of infinitely complex objects where the same patterns occur time and time again, but at different scales. And this is very much a contemporary area of mathematics. It's beautiful in the sense of mathematics and pure mathematics in its own right, but it also has led to numerous scientific breakthroughs in other related disciplines, not least through being able to analyze the growth of bacteria, analyzing brain waves, and, as we've just seen through the snowflake, patterns in freezing water. Thank you for listening. Diolch yn fawr. If you would like to find out more about studying mathematics at Cardiff University, you can visit the website or contact the school using the information provided.